Hi everyone, welcome back. The last video we discussed Freundlich adsorption isotherm, which is log x by m is equal to log k plus 1 by m log p. That is Freundlich adsorption isotherm. One point I forget to discuss, that is plot of log x by m versus log p. This is a straight line equation. So log x by m versus log p give a straight line. Log x by m log p. You get a straight line. Right? With the slope 1 by n. With the slope (1 by n) and intercept is equal to intercept, that is log k. Intercept log k and slope 1 by n. We get a straight line. Then not only that, for adsorption from solution phase adsorption, when the adsorbate is dissolved state and we are adding some adsorbent and adsorption takes place in solution phase, then instead of this pressure we are using concentration. The only difference is that instead of pressure we use concentration. So our equation will become x by m is equal to kc raised to 1 by m. Kc, instead of p it is c. So log x by m is equal to log k plus 1 by n log c. Again we are plotting log x by m against log c. We get a straight line with intercept slope 1 by n and intercept log k. We get the same straight line. So the adsorption isotherm, Freundlich adsorption isotherm is applicable in solution phase adsorption also. Then we are moving to our next adsorption isotherm, that is Langmuir adsorption isotherm. Langmuir adsorption isotherm. Langmuir, who won Nobel Prize for chemistry for his devotional work in surface area and surface reactions. He developed the theory and derived the isotherm using some assumptions. So first of all we just have a look into the important assumptions made by Langmuir. The first assumption, that is related to binding sites. Each surface contains a number of binding sites, vacant sites, that is sites to be occupied, and all sites are same. Sites are same. That means each site has similar affinity towards the incoming molecule. Okay, suppose this is a site, this is a site, another site, another site. All these sites are same. Then suppose a molecule is approaching to the surface, then all sides have the same affinity towards this one, towards this molecule, and it occupies one of the sides. So each and every side is similar and having similar affinity towards the adsorbate molecule. We call it as, these sides are vacant sites or bare sites. Vacant sites or bare sites. The second point, each binding sites adsorb only one molecule. One site, one molecule. That is, one site can accommodate only one adsorbate molecule. That is, this is the site. So when one molecule occupies this site, then no other molecule can occupy the same site. It is not possible. So one site can accommodate only one molecule. Monolayer adsorption. Monolayer adsorption. That means when adsorbate molecules come closer to the surface and get adsorbed on the surface, each and every vacant sites are completely occupied, then what happens? A monolayer adsorbate molecule is formed on the surface. A monolayer adsorbate is formed on the surface. No multi-layer adsorption is possible. That is, next layer, it is not possible according to Langmuir. So only monolayer adsorption is possible. Okay. Then the fourth one, no interaction between the molecules, between the adsorbed molecule, between the adsorbed molecule. The adsorbed molecules are present on the surface of the adsorbent. These are the adsorbed molecules. Even though they are close to each other, they have no intermolecular interaction. Just like our kinetic molecular theory of gases. There is no interaction between these two and so. Okay. So there is no intermolecular interaction between the adsorbed molecule. Then there are two processes. What are the two processes? One is, suppose this is the surface and molecule, three molecules are coming and they approach to the surface and occupy that position. Okay? That process we call adsorption. Right? So adsorption takes place. He called it as condensation. Condensation. First process is condensation. But remember, when molecules get adsorbed on the surface, those molecules have a tendency to remove or escape from the surface. That is, they have a tendency to desorb. Desorption may take place. That is, this molecule escape from the surface. So this process is adsorption and this is desorption. So the second process is desorption. He called it as evaporation. So condensation is nothing but adsorption and evaporation is desorption. Both processes are simultaneous. Right? So two simultaneous processes are there, that is condensation and evaporation. And ultimately an equilibrium is reached when the rate of adsorption, that is rate of condensation, become equal to rate of desorption or rate of evaporation. That condition is known as equilibrium. adsorption equilibrium. So then, at that condition, rate of condensation is equal to rate of evaporation. Using these assumptions, he made the adsorption isotherm. Remember, no interaction. It is actually no interaction between the adsorbed molecule. Actually, it is, I told you that it is just like that of our kinetic molecular theory of gases. So it is the adsorbed molecules, adsorbed gas molecules behave ideally. Actually, okay, adsorbed molecules behave ideally, right? So we are moving to derivation of the isotherm. Okay. So look this figure, right? The number of molecules dissolved, that is evaporated, that depends upon the number of molecules occupied, right? If there is no molecule occupied, there is no desorption. Only one molecule occupied, that is one molecule adsorbed, there is only one chance, that is only one molecule get dissolved. There are 3 molecules occupied, all the 3 molecules may undergo desorption. If 10 molecules are adsorbed, all the 10 molecules may undergo desorption, or just one molecule may undergo desorption. So a lot of chances are there. So rate of desorption, that is evaporation, depends upon the number of molecules already occupied. If the number of molecules occupied, that is adsorbed on the surface, is 0, then rate is 0. Rate of desorption is 0. Okay, rate of desorption is 0. Right? Remember that. Then rate of adsorption, that depends upon the vacant site available. Okay, suppose this is the adsorbent surface and number of sites, total number of sites is 10. Out of 10, 3 are already occupied. Again molecules are coming. Okay, then the next level, rate of adsorption depends upon the vacant site available. How many vacant sites are available? Only 7 vacant sites are available. Right? So number of vacant sites, that depends on the rate of adsorption, rate of condensation. Rate of condensation depends or proportional to available sites. Once all the sites are completely filled, then rate of adsorption becomes 0. According to this theory. Okay. Right? So suppose theta is the fraction of molecules or fraction of size adsorbed. Fraction of molecules adsorbed. Fraction of size adsorbed. Okay. Then obviously 1 minus theta is the available vacant site. For example, our total number of sites 10, of which 3 sites are occupied. So fraction of the molecules occupied, or fraction of the molecules, we can say fraction of the sites or fraction of the molecules. Why? One site can accommodate only one molecule. So both are same, fraction of the molecules or fraction of the sites. So fraction of the molecules occupied is 3 out of 10. That is the fraction. Right? 3 out of 10 occupied. Right? Then vacant site. What is the vacant site? Available. That is 7 by 10. How can you get this 7 by 10? Simply 1 minus 3 by 10. Suppose this is the fraction occupied theta, then obviously this is 1 minus 3 by 10. What is 7 by 10? Okay. Directly we can calculate, but mathematically we need this equation. So if 3 by 10 is theta, then 1 minus 3 by 10, that is 1 minus theta is, which is equal to 7 by 10, that is our available, vacant site available for further adsorption. Okay. Then, according to Langmuir theory, rate of condensation, that is rate of adsorption, we can put it as RC, which is proportional to available vacant site. Okay, available vacant site. 1 minus theta is the available vacancy. Not only that, adsorption also depends upon pressure. That is, condensation also depends upon pressure. As the pressure increases, rate of adsorption also increases. So we can say RC is proportional to P. Together, we can write RC is proportional to P into 1 minus theta. Right? Then rate of evaporation or rate of desorption, RE, which is equal, or we can say proportional to what? Number of sites already occupied. If there are 3 molecules occupied, all the 3 can be or may be evaporated. If there is no molecules occupied, that is number of fraction, that is 0. Fraction of the molecule occupied is 0, then evaporation is also 0. So it is proportional to theta. We can write it as, so we can write this as RC as is equal to, we are replacing this proportionality by a constant. Just put it as K1 into P into 1 minus theta, and it is K2 into theta. K2 into theta. Then at equilibrium, he assumed that RC is equal to RE, that is rate of condensation equal to rate of evaporation. That means K1P into 1 minus theta is equal to K2 into theta. K1P into 1 minus theta is RC, then K2 into theta is RE. At equilibrium, K1P at equilibrium, K1P 1 minus theta is equal to K2 theta. Just we are rearranging. This is very simple. Then K1P into theta, K1P into 1, K1P minus K1P theta is equal to K2 theta. Taking this right side, K1P is equal to K2 theta plus K1P theta. So K1P is equal to K2 plus K1P into theta. That is, theta is equal to what? K1P divided by K2 plus K1P. Alright? Then divide numerator and denominator by K2. So we get theta is equal to K1 divided by K2 into P divided by K2 by K2. No need of writing this 1 plus, enough. K1 by K2 P, which is equal to, okay, put K1 by K2 is equal to capital K. Then this equation becomes theta is equal to Kp divided by 1 plus Kp. This is our Langmuir adsorption isotope. Okay, this is the fraction of the molecules occupied. What is the fraction of molecules occupied? Number of molecules, that is amount of adsorbate, adsorbed on a definite amount of adsorbent. Simply, which is equal to x by m. Right? Which is equal to x. Theta is equal to x by m. So theta is equal to Kp divided by 1 plus K. Or instead of K, some textbook write another constant, that's for example Bp by, the same equation can be, you can have this one Bp by 1 plus Bp. Doesn't matter because K or Bp, it is constant. Then x by m, amount of substance adsorbed, it's actually proportional to theta, or theta is proportional to amount of substance adsorbed. Okay, amount of molecule adsorbed, or x by m is equal to k1, k2 is used, so k3 theta, but theta is equal to this one, so x by m is equal to k3 into capital Kp divided by 1 plus k2. Then k3 and k, you can put it as x by m is equal to k dash p divided by 1 plus k. Again the same equation, k where k dash is equal to k3 into k. Instead of k dash, you can put it as a, that is b. So the equation, some text can have it is ap divided by 1 plus bp. Doesn't matter, all these are constants, the notation may be different. Okay, so this is the expression for Langmuir adsorption isotherm. Divide this by p, or we get x by m by p, x by m divided by p, k dash p, so it becomes just k dash divided by 1 plus kp, that is k dash p divided by p, so this p and k dash p divided by p, that is the equation, so this and this cancel, so we get this one. Then take the reciprocal, so p by x by m, p divided by x by m is equal to 1 plus kp divided by k dash, or we can write this as p divided by x by m is equal to 1 by k dash plus kp by k dash. This is another expression of Langmuir adsorption isotherm, and a plot of p by x by m against p. We get a straight line. Okay, we get a straight line, that is p divided by x by m against p. We get a straight line with the slope. What is the slope? K by k dash. Slope is equal to k divided by k dash. Right? And intercept equal to 1 by k dash. Right? This is the intercept and this is our slope, k by k dash. And in solution phase adsorption, this equation becomes, instead of p, we put it as concentration. C by x by m is equal to 1 by k dash plus kc divided by k dash. So plot become C divided by x by m against C. We get the same plot and slope and intercept. So this is Langmuir adsorption isotherm. One more thing is to be discussed, that is x by m is equal to k dash p divided by 1 plus kp. Okay. Then at high pressure, what happened? Kp become very high, so 1 is negligible to kp. So x by m is equal to k dash p divided by kp, that is k dash by k, which is equal to constant. That is x by m is constant, independent of pressure. That is x by m is equal to, or we can say proportional to P0, independent of pressure. Okay, and at low pressure, what happened? Very low pressure, this term become negligible. So x by m is equal to k dash t, or we can say x by m is proportional to p raised to 1. We see these two conditions in our Freundlich adsorption isotope. So in between this high pressure and low pressure we can write x by m is proportional to p raised to 1 by n. So it is actually the Freundlich adsorption isotherm. So Freundlich adsorption isotherm is a special case of Langmuir adsorption isotherm for a particular range of pressure. Okay, it is a type of Langmuir adsorption isotherm or a special case of Langmuir adsorption isotherm. So Freundlich is just a special type of special kind of Langmuir adsorption isotherm. And we can have the equation from applying these two conditions. Okay. I hope the topic is clear. Thank you for watching.